Welcome to Computer Vision Decoded, where we discuss topics in the quickly evolving world of computer vision. In today's episode, we're going to dive into one of the hottest topics in computer vision. That's neural radiance fields, or as most people know it, NeRFs. As always, I'm joined by our chief scientist of EveryPoint, Jared Heinley, and today I'm extremely excited to have our first guest on the show, Matt Tancik. Matthew is currently pursuing a PhD in the Computer Science and Electrical Engineering Department at UC Berkeley. Last but not least, he's building NeRFStudio, a collaboration-friendly studio for NeRFs with a few other students at UC Berkeley. Thanks you two for joining. Just start off, I just want to get a little bit of a background. Matt, what set you on the journey of pursuing computer vision and your whole background that led you up to all this NeRF research?
Yeah, that's a good question. So I guess I first got a computer when I was in maybe middle school, an old hand-me-down laptop from my parents, and wasn't allowed to play or couldn't download games, right? But the one thing that it was able to run was Blender. So that was sort of like the first program I actually had access to and started playing around with. And I'd say that's kind of where it started. First internship I got was using Blender full time. Lots of reconstructing scenes from point clouds captured from LiDAR. And then going throughout undergrad, sort of switched to the more academic route, taking classes. Wasn't really sure what I would do after that, but realized that you could actually contribute to these cool tools like Blender and build off of them. So that kind of got me interested in what you actually needed to do to contribute, which is learn how to program, learn these various 3D graphics methods, and ultimately ended up here at Berkeley working on my PhD, where worked with a great group of folks on building out NeRF and the various variants since.
All right. I mean, look at your background. Prior to Berkeley, you were at MIT. Was that correct?
Yep.
All right. That's a huge difference. East Coast cold versus, the warm weather in Berkeley. I guess kind of warm, depending on what time of year. All right. And it's interesting. I don't come from the computer science background that you two come from, but it sounds like, you have similar backgrounds. Jared, what can you talk about yours too? Because I think that's kind of interesting how people end up in this really, it's kind of a hot field right now, but you don't just fall into computer vision as a research.
Yeah, no, it's similar. Like with me, it was high school getting my first graphing calculator, the TI-83 or whatever. And so there, I did put games on it, Tetris and, Space Invaders or whatever it was, and then very quickly was like, okay, how can I make games? And then trying to figure out programming and, how can I make 3D games? And then that led me on the path of, how can I do 3D programming? And then I, did my computer science degree, got interested in ray tracing research just to, render, really nice looking images. And then from there was like, okay, well, I can render images, and how can you take images and turn that into computer vision? So that was a big game changer for me, realizing that there was a whole world of computer vision that I had never seen before. But yeah, I'm loving the that graphics, that imaging, that Blender background. That's really cool.
Yeah. There's a lot of different paths to get where you are.
Yeah.
All right. So, Jared, do you want to tee up one of the first questions, or I can take it from here?
I was going to say, so for me, I guess, so my background, I deal with 3D reconstruction, a lot of image-based 3D reconstruction, but NeRFs, that's not I haven't done research into NeRFs, like you have. And so I guess just to start that off, can you explain to us at the highest level, what is a NeRF and how is it different from something that I'm familiar with, more like a photogrammetry-based output, whether that's a point cloud or a textured mesh? What is a NeRF? What does that even mean?
Yeah, so I'm going to start by explaining what a NeRF isn't. So what a NeRF isn't is a mesh. For people who are not super familiar with graphics, it's basically the way that almost everything that you see in 3D is represented. So the world, video games, TV shows, when they want to use 3D rendering, they'll use a mesh, which is just a scene that is made up of a bunch of triangles where each triangle has a different color. And if you think about why we use meshes, it's because it's something that we can actually easily or somewhat easily interact with. The world's quite complex, but we have to make some simplifications. So if I know that I have a flat wall, You could try to model it on like every single atom to describe the whole wall. That's obviously way too complex. So instead, I just create a big triangle, a bunch of big triangles, color it white in this case, and that's my wall. So this turns out to be a very easy thing for like humans to sort of work with. You just sort of move around the corners of these triangles. But for various reasons, it's actually kind of tricky for a computer to operate in that regime. Because the way that we want to sort of create these computer algorithms to reconstruct scenes, they will sort of start with some mesh and try to deform it or modify it until it reaches some target shape. And that's, you have to ask what question, like the question of what do you start with? So you could start with like a sphere, and then you sort of slowly deform it over time until you get, say, a water bottle that I'm interested in. Now, in this case, it's probably going to do a pretty good job, but you've got one problem here, which is like, there's this loop, right? Now, there's no way I can modify a sphere such that I still get that hole. So you run into these sort of edge cases and problems when you try to use meshes in the sort of computer, like having the computers operate with them. So for that reason, we're going to approach the problem from a very different approach, one that's maybe harder for humans to interact with, but easier for our machines to interact with. And this is more of the approach of like, let's try to model every atom in the scene. Now, in practice, it's not every atom in the scene, but it's like bigger chunks of space in the scene. So I think the closest analog is something like Minecraft. So Minecraft, you model the world with cubes, right? And you can draw them. You can kind of make whatever shape you want. People make rather crazy objects, but these are pretty big blocks. So let's just imagine Minecraft, but now we make the blocks smaller and smaller, and we can represent most things in the world. So we call this a volumetric representation because we're modeling the volume every place in space. So NeRF is a volumetric method that can represent the like realistic representations of scenes. Where some of the novelties of NeRF come in that sort of differentiate it from something like Minecraft is sort of along two dimensions. The first dimension is you want these really small cubes, or you want to be able to represent small regions of space. Turns out if you try to do it with something explicit, like a bunch of cubes, it just doesn't fit on the computer anymore. So you have to come up with a different way to describe the scene so that you can represent a very large scene. So I'm not going to go too much into the details, but a lot of the, like the original NeRF method will essentially use the same technology that machine learning uses, a neural network, to represent all these little, essentially, cubes in space. And then more recent methods kind of blend that with the Minecrafty approach of having actual cubes. And it turns out you can get some speed ups. And that's where you see a lot of these methods that can work really fast, kind of blend these different methods together. So that's one difference. The other difference is like the real world, the color of a point in space isn't constant. If I move around, it'll change colors, right? If you look at this water bottle from one angle versus the other, you get reflections and what we call specularities on these objects. So we want to make sure that as we represent all these little pieces in space, they have a way to change their color depending on the direction I'm looking at it. And that color that we're changing is one way to think about it is it's the reflectance or the radiance. Radiance is the color emitted from a particle in a certain direction, and hence the name neural radiance field. So it's a field. So a field being a space full of particles that are represented by these particles with different radiance. And we're going to use a neural network to actually store that information. So that's a neural radiance field.
Okay. So that makes sense to me. How about you, Jared?
Yeah. So to me, it sounds like it's a very, fundamental difference in the representation. Like you said, so a triangle mesh, you've got vertices, you've got triangles, you're representing sort of like these solid surfaces. There's empty space, there's a surface where that triangle is, and there's empty space behind it. And you're linking these triangles together to represent that surface or the boundary of objects. That being one representation. Another representation, I work a lot with is point clouds. There is no sort of representation of the surface. It's just a bunch of sort of independent samples of here's just a point in space. And there, it may not be on some sort of regular grid. It couldn't just sort of be random or sparse or there's going to be patterns to it, but that's, there's no representation of the surface. Whereas, saying here with this, volumetric representation, this is sort of a third, different representation that's representing, sort of the density or the radiance at all of these points in space. But yeah, that makes sense about having to, like a lot of the issues of it just trying to do a brute force and store all of that information at once, is way too much, and then having to deal with various ways of compressing or reducing that data to make it practical. Oh, that's cool.
Yeah, you mentioned point clouds. Like, one way to think about this is just a really, really, really dense point cloud, with the exception that the points can change color depending on the direction you look at it.
Yeah.
I think that view dependent, like the scene changing as you change the view of the camera is part of the magic that has kind of caught the imagination of all the creatives. And just, I post something online, and you're seeing shadows tracing through, or reflections tracing through water. I think that's what people are seeing there. Is you're changing the camera. Well, the appearance of that part of the scene has now changed, and you just don't see. We've not seen that any other way, except for a lot of manual work of people, doing things for like games where they have to, do a bunch of fancy tricks with meshes and textures and post production that. You're not doing that. I'm not doing any post-production on NeRF. I train the NeRF. I render a camera animation of the scene, and it just happens.
It's worth noting that these like reflection properties are something that we like hope the model predicts the correct reflections. But in many cases, there are ways to cheat. So using the same representation of space, there are ways to make it so that it looks correct through this optimization procedure from the images that you give it as input. But in practice, the thing it reconstructs, like the underlying density and geometry, is incorrect. And so this is one of the reasons why people do differentiate this versus existing approaches that are more focused on the actual geometry, because you can't really trust the geometry in NeRFs. And so one good example is something like a mirror. A mirror, you could represent the scene as having density at the surface, and then depending on the direction that I look at each of these points, it changes color. And that would be the correct way to represent it. There's another way that you could theoretically represent it, though, which is to represent it as a whole, that you look through the world and you see the reflected world like at the same depth that it would be if I were like looking behind me at that location in the mirror. And so the computer is kind of deciding during this optimization which one to choose. And there's ways that you can try to like force it to choose one versus the other by like tweaking some parameters. But in practice, like either one satisfies the goal that you give that computer to begin with. So you do get these like weird artifacts often. And on an artistic sense, it can be like quite compelling. I think people may have seen there's some videos people have made where they've done NeRFs of like mirrors and other reflective objects, and you can like fly into like the mirror world. But depending on your ultimate application, like that may not be desirable.
Oh, that's so cool. That's so cool. Like your comment there about, having it look good even though the geometry is bad. I mean, I see it a lot of times with textured meshes. It's like, oh, you can have a really low quality mesh, but then you texture it with some texture and all of a sudden it looks like it's amazingly detailed. This sounds like it's like that problem, just, to the next degree of it's, you can have this is, dealing with reflections and that whole thing about, well, is it the mirror actually that flat surface, or is there a mirror world, hidden behind that space? That's so cool.
I mean, it's worth mentioning like a little bit of the history here. So things like photogrammetry are interested in reconstructing the correct geometry of the scene.
Yep.
And when we started the NeRF project, we came at it from a completely different sphere. Our goal was, can we create good looking images? We didn't care about the underlying geometry at all, which is why we were like, let's just represent the world as this sort of like cloud. It's just a lot of little particles. There's nothing that forces it to be correct. We just care about pretty looking pictures in the end. And when we, like, if you look at the original NeRF papers, that is sort of what we focus on. Like, oh, we can get these good looking images out of it. It was sort of by accident that you can actually get pretty good geometry in many cases, and use it for other applications.
Neat.
Okay, so going down that line then of now you've built the first NeRF and you guys have iterated on it and improved it, or maybe not improved, but have different versions of it now, and that some of the geometry is appearing to look better. Do you see a future where perhaps photogrammetry becomes this deprecated model or method to create an accurate representation of the physical surfaces in the world, and we use NeRFs instead? Or do you always find that this will be kind of never reach that same level of accuracy that you would get? Are they is it kind of like that will supersede it, or there'll just be different methods that have different pros and cons?
I mean, I think there'll always exist multiple methods, but one thing that kind of surprised us is we released the paper, we got good looking quality results, but a lot of people are interested in the actual geometry. And so what you end up seeing is a lot of the follow-up work, particularly in the computer vision community, has focused on the geometry aspects. And that's why you do see that like there's methods coming out with much better geometry. And one thing to note is a lot of these methods will actually take in some of the ideas from photogrammetry, like things that we know work well in photogrammetry, import those ideas into NeRF in order to improve the geometry. So it's not that like one will supersede the other, but it'll be sort of a combination of merging that makes sense because,
No, I think that's valuable. I mean, just because that sharing of knowledge between the different approaches. I mean, I've seen that from just like the photogrammetry side, like using pure just heuristics and algorithms to let's triangulate points in space and then compare patches of pixels to see which one, what is the depth of this point. And so there's a whole decades and decades worth of literature about here's the best methods to do that. And now some of those are being superseded by learned based approaches where you can say, well, no, a machine learning method, neural network can do a better job at figuring out, well, given these two images, what is the depth of a particular pixel, and so you start leveraging the best tool for the job in that goal of reconstructing or understanding the scene.
I think one interesting data point, and this is by no means general, but one thing I've experienced when I have a lot of images that are well captured of a scene, and I have like good camera poses, if I also have additional depth information, say from a LiDAR scan, it's often beneficial not to take it into account. Because even though like LiDAR is very, very accurate, any sort of misalignment, which is almost guaranteed given that like you've got rolling shutter artifact, various artifacts that happen that misalign the images from the LiDAR, plus the surfaces of like the edges of objects with LiDAR can be sometimes kind of noisy. Not taking into the LiDAR into account when you have lots of images, you can actually produce better quality depths from images alone. So I think that's like a bit surprising. Again, it's not general, but in some cases that does end up happening. And so I think it's worth like asking when we think about how we do these like photogrammetry type setups where we do care about recovering geometry, like maybe there are other approaches that involve just like taking lots of photos and using NeRF-based approaches. Now, if you have something like a wall that is all the same color, NeRF and photogrammetry are gonna fail to produce like a good representation of that, where LiDAR is going to do quite well. So I found LiDAR type depths are helpful when you have scenes like that, or if you have cases where you just don't have very many images. But if you've got a lot of images, NeRFs can be kind of compelling.
Mm-hmm. When I've seen in my personal explorations of the hundreds of NeRFs now, I've just kind of thrown all kinds of different scenes in, and as you said, like it doesn't know where the sky is, so you end up if you don't look at it from the right directions, you see perhaps what would be a cloud over a building, and it's like the cloud is actually in front of the building if you were to look at it from the wrong direction, because it just doesn't know how to represent that scene from that angle at all. It just doesn't have that depth information. It says, oh, there's something there. I can't tell if it's, I'm guessing it just doesn't know if it's really far away. It's really close. But I find that if then all of a sudden I get more images, like if it's an unbounded scene, I get that. But if I manage to like walk around a building, it starts to say, oh, well, I saw it from the side profile now. And no, there is no cloud hanging out in front of that building. It's a blank space. It's transparent there. So it is kind of cool to see how you can change your image set to get less of that ambiguity of the radiance field there.
Yeah, because I mean, it produced the correct image for that viewpoint that is trained on, right? And so the trick is like, how do you also help make it produce good images from new viewpoints? And it does pretty well when you're like in the regime, like the same areas that you've captured from. As you deviate from that, you're going to start seeing artifacts like that. And then in a case like that, this is where like you can step in and say, well, we know that the sky or things up high like are often very far away. So you can start programming in some prior knowledge saying, okay, if I see something like that, put it as far back as possible. You have to be a little bit careful there, because now let's say we have some fixed color that like the blue sky, it doesn't change depending on how I look at it. So I can put it infinitely far away. But if I look at the ground, maybe it's like a nice new concrete ground. It looks the exact same color. I could also put that infinitely far away. So it becomes like a game of which sort of prior knowledge do you want to incorporate? And any prior knowledge that you do incorporate, it could potentially like hurt other aspects.
Yeah, so Jared would know that. There's a lot of balance and a lot of, as I've dove into the world of computer vision, finding out how much you guys just spend experimenting with different variables and just seeing how, run the data over and over with modifications to get that desirable effect for the hopefully known scene that you're going to be representing more than once, in the future, and say, okay, well, we know if we're doing this sort of scene, we'll use these parameters, and a lot of that's just trial and error. See how it ends up.
Yeah. So much goes into just understand, because you can develop algorithms. The ideal would be to develop an algorithm, a method that can work anywhere, under any environment, under any circumstances. But a lot of times having some knowledge about, I'm going to be reconstructing man-made objects, and so therefore there's going to be a lot of stuff that's going to be flat, or I'm going to be in an outdoor environment where there's going to be no repetitive structure. Everything looks unique and random. And I can sort of, use that as some sort of constraint, or, help influence the algorithms that are being developed. So, yeah, it makes sense.
All right. So I have some, Jared has some questions around Block-NeRF, which may be one of the more novel, or interesting ways that NeRFs have been used. That I think that one circulated the internet for a good while. I think it was interesting. Was it 360 images, 360 camera images as input? Is that correct? And is that how you see this technology for capturing large spaces to be more like a 360 camera array, or was that was you guys just something that was unique, that Waymo had lots of just different cameras all over that their cars that capture that data?
So you can kind of think of it as a 360 camera, but in reality it wasn't. It was, the car itself has, I forget exactly how many cameras, somewhere around 8 or 9 cameras that are placed looking in all directions. So in that sense, like you can fuse them all together to make a 360 render. The slight modification there, and this is an important aspect of NeRF, is you want to view the scene from as many locations as possible. A 360 camera, the camera sensor is at one location looking in all directions. So while you see everything, the source is the same location. The cars are a little bit different because the cameras are like spread across. I think like there may have been some on the like front bumper, or some on the top, some on the back. So there's a little bit of spreading as to where the camera sensors are. So it's a little bit better information than what you'd get with the 360 camera. That being said, if you just walk around with that 360 camera, you solve that issue.
Yeah, that's the same problem we have there in photogrammetry too. It's like, yeah, if you only have observed the scene from one position in space, yeah, you can't triangulate that depth, which sounds like that's the same problem there with NeRFs.
Yeah,
Yeah,
and
exactly.
I kind of pulled up the Waymo video, the video that, by the way, I noticed that you narrate a lot of these videos. Just to add a little humor here, do you guys draw straws? Who does that, or is that just who decides who narrates these papers? That's just something I've always noticed.
A variety of things. I mean, a lot of these are like who's still awake at whatever time of night before it needs to be submitted to a conference. But
All right.
Just,
well,
I mean, to take
you do really well with that. I just thought it was funny. It's like maybe they always make Matt go up because he's done a few of these now. Go ahead, Jared.
Oh, I was going to say, just to take a step back. I mean, so Jonathan's showing here these amazing visuals as just urban environments, downtown San Francisco or whatever being reconstructed. Matt? Can you just take a step back and just kind of explain at a high level? What is Block-NeRF, or what was the goal of Block-NeRF?
yeah, so the Block-NeRF was a project that was done with Waymo, which is Google's self-driving car effort. And their main goal is, essentially to make like autonomous cars to drive across all these streets. They can obviously test the cars on the streets, but they can only go so far, right? So if you want to start simulating new scenarios or whatever it might be, it's useful to have a 3D representation of the world that you can like interact with. And so traditionally, you would potentially hire someone to try to create 3D assets of all these elements. But in this particular case, you've got these cars with all these cameras on them. Can you just automate the process? That was the goal. And so you've got photogrammetry methods that could potentially work on it. I had experience in NeRF stuff, so it just seemed like a natural idea. Can we apply NeRF to the data that the Waymo vehicles have already captured to just reconstruct them? But this leads to a few challenges that we don't normally have, or at least the original NeRF papers didn't really deal with, and it's really one of scale. So while there's a lot of data that is of different regions of space, you have to take into account that they were taken at like different times, and that different objects were around. So a lot of that paper was just a matter of like pulling together various other approaches that have been proposed in other papers that kind of account for these different aspects. So things like changes in weather, things like there's a vehicle driving by, how do you handle all that?
Okay, that makes sense. And what you said earlier, talking about how NeRF's motivations being around generating that nice looking image, that realistic looking image, versus just perhaps accuracy or just raw brute force accuracy of the geometry. That makes sense if you're trying to simulate the world, and simulate the world through visual means. Having those really nice looking accurate images, that seems like a great application of NeRF.
Yeah, because these self-driving car companies, or most of them, like Waymo, they have LiDARs on them. So they have some estimate of the 3D geometry of space. And so simulating LiDAR, it's not easy, but it's a little bit more straightforward. And that's something where you can actually use more crude 3D models that already exist, that you can just like create a LiDAR sensor and just have it travel through that space. Visual is harder, right? What actually is fed into the camera, you want it to be something that looks photorealistic. Now, I think the video that you were just showing is a step there. It's not photorealistic yet, right? There's issues, and a lot of those issues come down to the fact that this data was captured over long periods of time. And so you lose some of the constraints that you normally have, or assumptions that you normally have, that like the scene is static. So when the leaves on the trees change, we don't really have a great way to account for that. So as a result, it sort of blurs it all out and kind of predicts the average of all the different leaf positions. Or when you look at this data over a long enough period of time, you actually see like the tree grows, right? So
depending on what view you're looking at, the tree is either short or tall, or
no, like literally it grows over a month or two period of time, right?
Oh, okay.
So, or the leaves fall off the trees.
That's cool.
We did have a past episode about computer vision in the wild, I think was the title, and it was those challenges. So Jared has a lot of experience as well with just crowdsourcing hundreds of thousands of images, and it's just no matter what, you're not going to get perfection, but it's amazing what you can pull off to get a good understanding of a scene, even with all that mismatch of information between images. Jared was even using a mix of cameras that we didn't even know what they were scraped from PhotoBucket, I think, or one of the big crowdsourced image sets where you didn't know what the camera was, you just had images. So it's impressive what he pulled off, especially also that Block-NeRF was done. That wasn't done like last week. That was a while ago. So, not that you can solve those problems necessarily today, but, I've already seen the quality of NeRFs just improve as this has evolved. And I think people forget. They say, oh, well, this is not as good as photogrammetry. Well, photogrammetry's been around since, decades versus a couple of years. So there's a lot to figure out, a lot to optimize. So I just thought was a really good example of how, kind of like you said, you pulled in a lot of ideas to pull off this large NeRF. So one thing I noticed that people kind of struggle with NeRFs is it takes an enormous amount of GPU power. You can't just run it on a entry level laptop or desktop. You need that high end GPU. Can you talk about that? Like, do you see that burden goes away in the future? Is that just the reality of the technology? And if so, also how do you expect people to be interacting with NeRFs? Are we going to be doing it on cloud-based environments where you don't have to? It's just close, hosted out there in the cloud. How do you see that moving?
Right, they are compute intensive, and maybe I'll briefly describe why they're compute intensive. I described that you represent the world as sort of lots of little cubes, or like little chunks of space. But since it's all being represented in sort of this representation that often is like a neural network, you don't actually know where it is until you ask whether there's something in that location in space. So the way you actually render or predict the color of a single pixel is you sort of like shoot a camera ray out into space. And then along that ray, you take lots of little samples. And each of those samples, you ask, is there anything here? And if there is, what color is it? That asking process is actually feeding that sample through a neural network and popping out an answer. And so if you're doing 500 samples on array, 500 queries of a neural network, and you're trying to render a 1 megapixel image, you're rendering, like, evaluating this neural network billions of times. So very quickly it becomes quite expensive. And for that reason, the original NeRF papers, they would take almost a day or in some cases more than a day, just to reconstruct a single scene. Quite expensive. And for a while, that was like people were sort of fighting, getting it maybe like 20% faster or 30% faster. But over time, people found more and more tricks in order to make it so now you've got something like instant NGP or these other fast methods that can train on the order of 5 minutes, right? So we've already gone multiple orders of magnitude. There's different ways and different tricks that people use, but one of the biggest tricks is instead of doing 500 samples along the array, if you keep some information around saying that, like, there's nothing here, don't sample this region, you can get rid of most of that computation. And so as we go forward, we're coming up with more and more tricks like that so that we don't have to do quite as much computation when we actually render the scene. So do I think it's going to get faster? I think it will. I mean, it already has gotten significantly faster. That being said, it's still obviously not something you can run on your laptop, but I do think it'll go farther. I think the other thing that's worth mentioning is computer graphics, 3D graphics, we kind of take for granted now, but it took time for them to actually be feasible to run. And one of the main reasons they're feasible now is because we have something like a GPU, which is literally designed to render out a bunch of these mesh triangles as fast as possible. So we're sort of seeing people get more on board with these NeRF-based methods. I think it's totally feasible that these manufacturers will also start looking into, like, how do you actually optimize on a hardware level, rendering these things out faster. So that base approach, I think, will continue to get faster. It might be a little bit slower, especially if given that like hardware modifications may be necessary. But there's another approach that you can kind of look at, which is can we convert these NeRFs into something else? So if we forget about the actual creation of the NeRF for a second, let's just say the creation of the NeRF stays a bit expensive, and that's something that you run in the cloud or somewhere else. Once it's created, people are coming up with more and more methods to convert it into a representation that still maintains a lot of the visual quality, but is using the technologies that we've already optimized, essentially converting it to a mesh or something similar to a mesh that we can run on something like a phone or normal devices without GPUs. And we already see that happening both in research and also in industry. Luma, for example, is a company that will do some sort of conversion like that, which is why you can visualize it in your browser.
Mm-hmm. That makes sense. I also saw mobile NeRF, which turned it into a triangle mesh as well.
Yeah,
running high FPS even on my my iPhone in browser. So
I just as like a interesting aside is like mobile NeRF, it converts it to a triangle mesh, but it's not a triangle mesh that you're used to. What it is it's tons and tons of triangles all overlapping each other. Like we like to use the term triangle soup, where it's just sort of like you splatter triangles into the scene. And so it's not the way that people typically think of triangle meshes, where a lot of people care about it being watertight. So it's some volume that doesn't have any holes. It's like nice and perfect. That's not what these are. But they can leverage the advances in GPU technology to make it really, really fast while also producing great looking renders.
Yeah, that's what I noticed. It looks great. Don't leave the scene. It's not ready for a game. And also a lot of triangles. It's not optimized to be the best looking with the least amount of triangles and meshes and data there. It's but it works. That's interesting for visualization. And I think a lot of people forget that NeRFs. There's a lot of people say, well, what's useful with the NeRF if I don't get a mesh? There's no use for this technology without meshes. And that is definitely a viewpoint from people who just need meshes. They work in game engines, they work in software that they're interacting with a mesh, and that's fine. But I think that people just overlook a whole entire, like think of Waymo, they're doing self-driving cars, right? So they actually don't care about a geometry a lot of times in a scene. It's the cars learning what the scene looks like and how to interact with a scene based off appearance, because using camera guidance. They're not and you can simulate LiDAR data for some geometry, but I think that is a application where we don't even have to worry about meshes, and it could be expensive to render and expensive to train, but we're using it for these machine learning models that in the end, it's worth all that investment, all that time, all the energy, all the GPU cycles, because it actually is faster than someone perhaps modeling these objects in 3D in all these third-party softwares just to get one little scene for a car to learn how to drive around it. So I just think to throw that out there.
Yeah, I think I would also have sort of like two other responses to someone who says they just want meshes because they want geometry. I think that's totally valid because that's what our tooling is built to use right now. But so the first thing is people are creating methods to convert NeRFs to meshes. So it's not like using a NeRF means that you don't get something like a mesh as an output, right? Not quite as good, but we're getting better, and there's a lot of research in that space. So I wouldn't be surprised if you can get pretty good meshes out of a NeRF-based model soon. And the second thing is people want meshes because that's what their tools currently use, right? If you got the Unity game engine or whatever game engine, you import a mesh. I don't think that's always going to be the case. You've already seen people hack together ways to import NeRF-style models into these existing game engines. And I think it's only a matter of time before these game engines implement it at more of a core level. So once that is the case, then do you actually need the mesh, or you just need the mesh because that's what your current tooling uses?
Yeah, I agree there. It's a necessity right now, but is it a mandatory requirement? Maybe not. And I've been spending a lot of time interacting with NVIDIA, who obviously are spending a lot of time and energy and research cycles on this technology, and they haven't said anything publicly, but you can tell that they're working on something with the Omniverse off of what they've said, and I can only imagine that they're going to have some sort of server-based rendering of NeRFs and not convert it to a mesh necessarily, because that the whole Omniverse, they have a lot of synthetic data rendering and things like that they use for machine learning, and I could see how this just easily integrates in that whole ecosystem where you don't need the mesh in that tool set. But like you said, some other tool sets, it's the reality of today.
I think there's also like a just general trend of a lot of tool sets migrating to the cloud. And once you migrate to the cloud, then they can do whatever they want in the back end, right? Like they can use all the compute they want. And yeah, so.
Yeah. All right. Well, I just want to pivot. I want to make sure we have enough time here because we're coming to the end of our time with you. But I want to make sure we talk about a project you're currently involved in called NeRFStudio. And I'm going to just, if people are on the YouTube version of this, I will, again, have some visuals of just outputs from NeRFStudio. But can you just give us a quick overview of what NeRFStudio is to start out with? While I show some cool, interesting results.
Yeah, so it's an open source project that essentially tries to bring together a bunch of different NeRF methods. So NeRF came out a little over 2 years ago now, and since then there's been a lot of follow-ups. The most notable ones are the ones that make it like real time and fast, but there's also been a lot of things to improve the quality in a variety of different scenarios. And the challenge is if you go out there and look and you just want to use NeRF, say you're a researcher or a programmer, it's not entirely clear where you start. You could grab, like the thing that I would recommend, number one, is don't grab the original NeRF code base. There's like zero reason you should use that anymore. Yet a lot of people still use it, and we still get like GitHub issues and people trying to mess around with it, but it's out of date. These things have improved since then. And I've personally experienced this. We talked about Block-NeRF earlier. Block-NeRF, I just combined a bunch of different methods together, right? And there was a few methods that I hadn't had the chance to combine yet. And so when I went back to Berkeley to work on my next project, I wanted to do essentially Block-NeRF, but on a academic level compute rather than like Google level compute. And I think it's possible now that we have things like instant NGP, which allows things to be quite quick. And so I started hacking around. I wanted to reconstruct the campus here at Berkeley. And very quickly, I realized I was repeating all the same things I was doing, like combining these different methods that I had to do when I was at Waymo. And it seemed kind of like a waste of time. And just thinking, there's got to be other people that are also trying to combine all these different methods together. What if we just do it the correct way, or a more correct way, so that when people want to use these methods in the future, they can just piece them together more like Lego blocks and get good results. At the same time, can we make the UI and usability easier so that folks that are maybe less into the research side of things can use this as a tool that combines the best of the best that we have in NeRFs at the moment? And so I, with a few other grad students, I'll highlight Ethan Weber and Yvonne, we worked together to create this, and we released it a few months ago. And yeah, it's been exciting to see other people use it. We released one model with it, the NeRFacto model. And so this is just an example where we combined a few different methods. So you asked, I don't know if you asked how it like compares to instant NGP, but like if you compare it to something like instant NGP, the new model is essentially instant NGP, but like with other things added on top of it. So it's not like it's trying to compete with it. It's using those ideas and concepts and just bringing in other ideas and concepts that have happened in the space since. So for example, now there's like a method that lets you render stuff in the background a lot clearer. Mm-hmm. Why not include that with instant NGP, right?
That was the first comparison. I took the same image set. I was like, I just want to see the difference between NeRFacto and instant NGP. And it was just like, oh my goodness, it's like the background mountains just snapped into clarity, which excited me because I always felt like things get further and further away. They almost look like they've been watercolored into the background, as opposed to just even out of focus. They just look smeared. And that's not the case.
Yeah. So the goal going forward, though, is as new methods and new techniques come out and like people sort of agree that this is like a good direction to go, we want to incorporate them and make an easy place for people to like contribute their own modules, but also sort of leave like a history of what sort of the different approaches one can take. And I think what's a little bit different than maybe treating this as like a traditional research project is that we're kind of doing this all in the open. The goal isn't to write some paper, and I think there's great reasons to write papers about different methods in this area. But I think there's equally good reasons to try to do these things more publicly and not just try to figure out ways to like differentiate yourself from others, because I think you got to accept that like there's a lot of good ideas in this area. If we combine them all, we can get something better. And so as a result, we've seen people outside of our core team starting to contribute to the repo, which is the thing that we like. That was our ultimate goal, because the hope is to make this something that's like sustainable, that people across industry and academia can help contribute to improve it over time.
All right.
That's such a valuable effort. I mean, like I know just in my work during my PhD, like, okay, every grad student, they've got their own project that they're working on, and I want to go try to use someone else's code. Sure, I might find it somewhere, and then I try to download it, compile it. Oh, it doesn't work, and so just that effort of just reproducing everyone else's work to try to build benefit your own. I really appreciate these problems. Like for me in the photogrammetry space, dealing with, CallMap or OpenMVG or Visual SFM. So some of these projects where it's like, oh, I don't need to reinvent an entire photogrammetry pipeline. I can take one that's already out there and then build upon it and extend it, or just use it just to see like, hey, what sort of results do I get out of it? So this project like NeRFStudio, where you're saying you're able to take, all these sort of state-of-the-art methods, make it modular, so that both researchers as well as engineers can give it a try, extend it if they want. That's such a valuable effort.
Yeah, I find this interesting because it's a project that excites Jared. An actual engineer, someone who can jump in the code base, and then someone like me who just checks on it every now and then, stays active in the Discord, and one day you're just saying, hey, pip install or pip upgrade your code base, and all of a sudden I got these new features, these new methods I can play with, and I don't have to add to the, I don't have to be committing to the GitHub repo. I don't even have to build the source code from scratch necessarily, like I did with Instant NGP. You guys made it easy and very, very tangible, way to use it. So it's kind of crosses the, I would say, armchair, quarterback, just want to go in there and play with it and see what it can do. And then, Jared, who's like, no, maybe we want to take some serious looks at modifying this and adding to this stack of technology. So how would someone find this? I mean, I can bring it up on my screen, but is this?
Yes, I mean, you should be able to just Google NeRFStudio, and hopefully the SEO is really high enough. The website is NeRF.studio. And
easy. I'll make sure I link it in all the show notes to all these, the podcast and YouTube video. But do you suggest they go here, which I have my screen? If you're on the YouTube, you can see I kind of have the web page pulled up. You start here and not at the GitHub level.
Yeah, I think starting. Well, I mean, you can quickly get to the GitHub from here, but hopefully you don't have to go to the GitHub if you don't want to. Like we want to be accessible for people who don't need to do anything coding related. On the left side, we've got something for installation. If you walk through the steps, hopefully you could be up and running. Takes a little bit of time to install, but once it's installed,
not that long though. So I hope to make a guide on getting this installed for the people who've never even touched command line. Just take it down to the very simplest core there. But
it's also worth noting that we do want to make this more accessible to people who don't have GPUs. So in the top left, there's a button that says Colab. Clicking that will actually launch a Google hosted program that gives you essentially free compute. Now it's not going to be top tier compute, so it's a little bit slow going through it, but it will allow you to replicate these results without shelling hundreds of dollars for your own fancy NVIDIA GPU.
If you can even get a hold of one, that's,
Yeah, if you can even get
there
one.
was at least on the 4090s, I think there's a thread of people just looking for when they get go on sale. So, well, anyways, I've taken enough of your time today. Just want to wrap this up. So again, it's NeRFStudio. I know that there's also a wonderful Discord channel where people are engaged and asking questions and answering them. And I mean, that's one way to get a hold of you, Matt. You're in there very actively. I notice responding to people, explaining things, and we're all grateful for that. It's rare that there's a research or some sort of this level of novel technology that you can just go and ask questions on a channel and get the actual researchers to respond. If it's a big company, a big corporation, a lot of times you're not dealing with the people closest to the software. It's some sort of representative who's asking you a question, then going and trying to answer it. So that's quite exciting. How else can we follow your work, Matt? Are you active on social, or your website? That's a better place to follow.
Yeah, so I mean, my personal website's just mylastname.com. But for all the NeRFStudio stuff, we've got @NeRFStudio team on Twitter where we post updates and renders. I think that's probably the best bet.
Great. I'll make sure those are all linked in the show notes as well, so people can find different places to see what you're up to and follow this journey at NeRFStudio. And as always, again, just thank you, Matt. And if you are listening or watching this before November 17th, Jared and I are actually going to host a live Computer Vision Decoded event in Durham, North Carolina, where Jared, his headquarters is. And we're actually going to show off just NeRFs and talk about it a little bit. And Matt, you don't know it, but we're gonna use NeRFStudio because I think it will be great for that community to say, hey, here's NeRFs. If you don't know about it or you're interested in it, go look at this. We're also going to use the Record 3D, both workflow you have, so we can just capture someone and within a few minutes, maybe the time it takes to transfer the data and initiate a line of code, we can have a NeRF training, which to me is really exciting too. Because, it's like one thing to say, okay, we took pictures, and in 30 minutes after we get all the pose estimations, we get to start training. Well, now we can skip that. So really excited. We'll make sure we share how that goes as well with you, Matt. So thanks, Matt. Thanks, Jared, for being on this episode. And I look forward to seeing you guys all in the next one.
Yeah, thanks for having me on.
Thank you.